Should I go ahead?
Yes, you're all set.
Oh, thank you so much. That was a great introduction. Hello, everyone. I am so excited to be here today to talk to you guys about my research in advancing energy security in situ 3D neutron and X-ray imaging diagnostics for electrochemical systems, primarily batteries. Sorry, there's a bit of a background noise. Do you guys want to mute yourself or?
Yeah, we can.
Okay, thank you. Sorry, that's much better. Yeah, you guys can hear me, right? Okay, so I will get started, and I want to start with a bigger picture overview of a world we want to live in. A world with reduced CO2 emissions, a world with reduced global warming, a world that is sustainable and has global energy security. Now, this is a word worth striving for, right? And mass market adoption of electric vehicles is a way to make this word a reality. Now, electric vehicles or EVs can provide us with a sustainable future. For example, if we look at this data here, you can clearly see that the life cycle global warming emissions from a mid-sized battery electric vehicle are around 50% lower than those from a mid-sized gasoline car. And most of this reduction is coming from the operation of the car itself, despite the 15% emissions that are associated with battery manufacturing. Thus, this data clearly shows that EVs can provide us with a sustainable future. However, if you own an EV today, you also know that there are many problems associated with them. For example, here I'm going to give an example from my PhD work when I used to drive from Stanford to LA. You can see that when you're driving from Stanford to LA in an electric car, you need to think about the charging stations to stop at. But most importantly, you need to factor in the charging time that is required to charge your EV in this 6 to 7 hour long journey. The speed of charging is one of the top problems faced by EV consumers today globally, according to the report from McKinsey. And extreme fast charging of electric vehicles is a potential solution towards this problem. However, we also know that the present day lithium ion battery technology, especially the one containing graphite electrodes and NMC cathodes and liquid electrolytes, they suffer from key degradation mechanisms during fast charging. So here I'm showing a schematic of a lithium ion battery where you can see we have a positive electrode, a negative electrode, and a separator. Now, what happens during charging is we are moving lithium ions from the positive electrode through the electrolyte and separator towards the negative electrode, which in lithium ion battery is mostly graphite. And here, lithium ions then get stored between these layers of graphite in the form of stored electrochemical energy. Now, when we are discharging the battery, we are moving these lithium ions back from the negative electrode towards the positive electrode. And now when we charge the battery really, really fast, what we are doing is we are moving these lithium ions really fast from the positive towards the negative electrode. And what happens during that process is lithium plating, which is given by equation 2 here, it dominates over lithium intercalation, which is what should happen, where lithium gets intercalated between these layers of graphite. And you can look at the electrochemical potentials of the two reactions. They're pretty close to each other. And hence the fast charging creates dominant or favorable conditions for lithium plating to dominate over lithium intercalation. Here I'm going to show you these optical images of two custom-made battery pouch cells that were charged between 10 and 15 minutes. And you can see deposition of this whitish material on the surface of this battery anode. So this whitish material is lithium metal or lithium deposits. And this process is given by lithium plating. Now, if you look beyond lithium-ion batteries, if, for example, if you look at solid-state batteries, which is what I'm working on in my postdoc at Princeton, they also suffer from plating-driven chemomechanical instabilities. Now, what do I mean by these fancy terms? Let's look at the schematic of this anode-free solid-state battery. It's anode-free because it doesn't have any anode, which means it only has a current collector in the form of stainless steel or copper or what have you. And plating happens on this current collector. So you can see in this schematic, we have lithium metal, solid state electrolyte, hence the solid state battery and this current collector. Now what happens during charging is that we move lithium ions from the lithium metal through the electrolyte and then plate at this interface of stainless steel metal and solid state electrolyte. And during this process of plating, you can see there's highly non-uniform lithium deposition, which results in fractures that form inside the solid state electrolyte, creating space for lithium to penetrate. Now, lithium penetration and this fracture formation are some of the key degradation mechanisms that happen due to plating in solid state batteries. Therefore, in my research during my PhD at Stanford and now during my postdoc at Princeton/Oxford, I am investigating where does lithium play in XYZ and how does it progress on the electrode during battery cycling. Now, this is a very broad research question which needs to be investigated in situ in 3D. Now, why investigating this question in situ in 3D is so important in a full cell battery? Because when you take batteries apart, sometimes there are electrochemical processes that don't survive disassembling. As simple as that, per Professor Claire Gray in her recent MIT lecture. And we need to have 3D information because 2D information alone can be misleading. Now, let's look at the schematic of the battery one more time. We have, current collectors here, graphite anode, transition metal oxide cathode, separator, and this is the interface where lithium is hypothesized to start plating and grow in the form of these deposits, then poke holes through the separator and result in battery short circuit. Now, investigating lithium plating or this lithium deposition in 3D in situ, so difficult because visualizing this interface in situ in 3D in a full cell battery, especially at these relevant micron length scales, extremely challenging in itself. Now, my approach to address this challenge uses in situ 3D neutron and X-ray imaging modalities. Now, let's look into why. These are non-destructive probes, and the way neutrons and X-rays interact with matter is encapsulated by the simple Beer-Lambert's law. Here you can see I is the intensity through the sample, I naught is the incident beam intensity, T is the material thickness, and mu, which is very important, is the attenuation coefficient. Now, this is the material's property. Now, for neutrons, this mu is directly proportional to sigma total, which is total neutron cross-section. Now, let's look at this part of the table. We can see that we have graphite, copper is a metal, and lithium, which is what we want to investigate. You can see that sigma total for lithium is very high, which means neutrons are very sensitive to detecting low Z materials like lithium. Now, if you look on the right side of the equations, you can see this mu for X-rays is directly proportional to mu m, which is a mass attenuation coefficient. Now, this mass attenuation coefficient for copper is very high, which means X-rays are very sensitive to detecting high Z materials such as copper. Thus, the idea is to use the sensitivity of neutrons towards low Z materials like lithium and X-rays towards high Z materials such as copper to identify both the low Z and high Z materials in a battery in situ in 3D without opening it. So the first technique that I developed during my PhD at Stanford was simultaneous neutron and X-ray tomography, which is a non-destructive imaging modality that provides 3D visualization of electrode degradation in a battery. As I just mentioned, X-rays are sensitive to high Z materials and neutrons to low Z materials. So this technique gives us complementary data by the interaction of the two imaging probes with matter. So I performed these experiments at BD2 Imaging Beamline at NIST Center for Neutron Research before NIST shut down. Schematic of the beamline is shown here. You can see in this schematic, we have a neutron beam, which is produced by a neutron reactor, and we have a microfocus laboratory-based X-ray source, which is producing an X-ray beam. Now, the neutron and X-ray beam here are roughly perpendicular to each other, and they hit the sample at the same time during the imaging experiment. And then we have a neutron detector and an X-ray detector that detects the neutrons and X-rays after they have interacted with the sample, providing us a neutron and an X-ray image. Then I take the data from both of these neutron and X-ray images to do dual segmentation, dual mode segmentation. And you can see here in the 3D visualization of pristine electrode, we have copper, which is yellow, and pink, which is graphite. So we can identify both of these materials at the same time. And this visualization shows that the two strips are on top of each other with no sign of degradation. But if we compare this visualization to that of the fast cycle electrode, we can clearly see delamination of the graphite from the copper current collector. We can also see this giant lithium containing protrusion, which can be directly correlated to this whitish deposit that I showed you a few slides ago, right? On this graphite, which was as part of a battery pouch cell that was cycled to death. So you can see here that using simultaneous neutron and X-ray tomography, we were able to visualize lithium and on a copper current collector at the same time. And because this is 3D data, we can also correlate these certain colorized segmented slices as a function of depth of the electrode. For example, what I mean by that is here slice A corresponds to thick yellow and white lines labeled A on either side. Same goes for B and C, where we can visualize this lithium containing protrusion very nicely. And in D and E, where we are going away from this protrusion, you can see the delamination of the current collector from this graphite. Now, during my postdoc at Princeton, I extended the use of this technique to anode-free solid-state batteries to understand how mechanical instabilities, such as fractures, are driven by lithium plating in this type of battery system. So I designed and machined the battery at Princeton and then shipped it to ILL in France, where the experiments were conducted. You can see here, I'm going to show you the neutron and X-ray data. So this is the X-ray reconstructed slice of a pristine cell, which means the cell was in the pristine state with no cycling. So this image clearly shows that there are some existing fractures in this pellet. And if you look at the images of the two batteries that were charged at a low and high current density, we clearly see that there are some fractures which are widening, just showing a potential correlation between fracture widening or mechanical instabilities and current density. Now, if you look at the corresponding neutron images, the first thing you would notice is in this neutron image, we can see lithium electrode, right? Because neutrons are sensitive to low Z materials like lithium. We can't see any lithium in the pristine cell, right? But the contrast to segment the pore space from the solid state electrolyte is much better in the X-ray imaging data. And that's why we do simultaneous neutron and X-ray imaging to be able to get this dual information. So in the pristine cell, we can identify the current collector, the lithium metal electrode, the solid state electrolyte pellet. And now if you look at the images of the low and high current density, you can clearly see that lithium is penetrating these fractures and its behavior is different at two current densities. For example, at low current density, I'm calling it filament-like lithium plating or deposition on this current collector as compared to the flow-like, where it's kind of creeping lithium through this giant fracture at a high current density. So I just finished the second phase of this experiment 2 weeks ago in France to wrap up this story. But this data clearly shows that we can hopefully decouple electrochemo mechanical instabilities and see which one is happening because of electrochemical current density or just the mechanics. The third example I will provide of in situ diagnostics is that of detecting lithium after fast charging and in its different morphological states. This experiment was done during my PhD at Stanford at Paul Scherrer Institute in Switzerland. So here you can see 3D visualization of plated lithium at 1C, which is a relatively low charging rate. So you can see here the visualizations are at 6C, which is a very fast charging rate, or like 10 minutes of charging. So the first thing that I look at this data, I notice is when lithium plates, it doesn't plate like a chunk of lithium metal. It does have certain degree of porosity associated with it. For example, you can see these nodules of different degree of density. And sorry, I didn't explain the difference between plated, dead, and active lithium. So dead lithium is the one that is irreversibly plated, which means this is the main culprit. There is no way this can go back to the cathode during battery discharging. And active lithium is the one that is still active and is electronically connected to graphite. So distinguishing between what parts of the battery forms active versus dead lithium is extremely important to understanding battery degradation, so that we can understand spatially how to engineer the battery in such a way that we can minimize dead lithium. So for example, this data clearly shows that there are these protrusions, which are lithium, like these tiny sharp light, which are forming like around this edge at faster charging rate, and they are absent or minimally present at a lower charging rate. And they are parts of the battery which form no dead lithium or very minimal active lithium. And they are parts of the battery that form low and high active lithium. So this data clearly demonstrates 3D spatial heterogeneities in the formation of plated, dead, and active lithium, and also morphological differences between low and high charging rates. With this, I would like to briefly talk about the two additional techniques that I'm developing right now with Princeton-Oxford collaboration. So these proposals were submitted last year to Diamond Light Source, which is DLS, and ICIS Neutron and Muon Source. So the first technique that I'm developing is operando X-ray imaging guided diffraction. With this technique, I want to investigate this fundamental question: is it even possible to characterize interfacial strain at solid-solid interfaces and then correlate it with mechanical instabilities? And per the UK Scientific Council, this experiment is very, very challenging. In fact, I just finished this meantime 3 weeks ago here at Diamond Light Source. And the second technique that I'm developing is operando neutron time of flight radiography. And with this technique, I want to investigate, can we monitor and map strain within the bulk electrolyte, not at an interface, but at the bulk electrolyte in 2D as a function of time as the battery is cycling. And again, per the Scientific Council, this is a very high risk and high reward experiment. So I'm really grateful to both Princeton and to the University of Oxford Department of Materials for betting on these ideas and helping me finish these crazy experiments. So the ICIS experiment is coming up in the next 3 months. And the Diamond experiment just yielded 150 terabytes of data. So I still have to process it before I can show you guys the results. And with this, I would like to acknowledge my PhD advisors, Professor Mike Tony, Dr. Johanna Nelson-Becker, and Professor Janan Bao from Stanford, SLAC, and University of Colorado Boulder, Professor Vanessa Wood from ETH, and Dr. Anders Keisner and Professor Marcus Strobel from PSI for helping with the PSI experiments during my PhD, and especially when this shut down. And from Princeton, I am very, very grateful to Professor Craig Arnold and Professor Claire White for really helping me embrace the interdisciplinarity of my work, which bridges neutron and X-ray diagnostics with electrochemical systems and believing in my science. And from the University of Grenoble Alpes, Dr. Claire Villaville and Dr. Alessandro from ILL for helping with the ILL beam time. The data that I just showed you. And from Oxford, Professor Peter Bruce and James Marrow for hosting me and helping with the Diamond experiments and the upcoming IMAT or ICIS experiment. And I have a very long list of collaborators who are professors, students, national lab scientists to thank, without whom this work would never be possible. I also have a very long list of neutron and X-ray facilities around the world, almost every facility that helped with these experiments. In terms of funding, I have to thank Stanford Dare Fellowship, Faculty for the Future Fellowship, Edward G. Weston Research Fellowship from the Electrochemical Society, Princeton Presidential Fellowship, and the ECS Colin Garfield Fellowship that funded my travel to ILL. And most recently, the Andlinger seed grant, and for giving me an opportunity to share my work. And with this, to shaping the future of energy security using in situ 3D neutron and X-ray imaging diagnostics. With this, I would like to thank you all, and I'm happy to take any questions you may have.
Thanks,
Yes, hello everyone. I'm going to talk today about some work I've been doing on a project called the speed limits of the energy transition. In particular today we'll look at capital discipline. I'll explain what that is, and then I'll give a hint to some of the other things we're working on as well. So yeah, what are the speed limits to energy system transformation? We'll look at capital discipline, and then our plans for interrogating different speed limits of the energy transition. So the speed, scale and the complexity of infrastructure transformation that's implied by our mid-century net zero goals is historically unprecedented. We use energy system modelling to influence the design of policies and incentives to support those goals, and to give us some level of confidence that we can attain those goals within a certain time frame. In this country and other similar countries, we're looking at mid-century for net zero, or at least there are goals. But the actual getting there is proving a challenge in some areas more than others. But we use modelling to look at how we can get there. Big modelling studies like was done here at Princeton, the Net Zero America study, and then a whole bunch of other IAM kind of modelling to look at what needs to be done to get to net zero emissions. Those modelling frameworks typically simulate rational entities operating across the full energy and industrial ecosystem with seamless and transparent cooperation. They have perfect foresight across decades and across other sectors. And interestingly, they typically simulate transparent and instantaneous conception, development and construction of the assets that we need to get to net zero. But in reality, those characteristics are mostly absent. As an example, we can look at the transformation of electricity systems globally. This plot shows for wind, solar and nuclear annual net capacity additions, and then the cumulative capacity additions of those technologies across a few different countries. And you see that transformation, while it's occurring, doesn't happen in a continuous way. The speed of transformation, so annual capacity additions, goes up and comes down due to numerous real-world factors. In Germany, over a certain period, there was a lack of land for construction, investor uncertainty and licensing delays. That caused a slowdown in the deployment of wind and solar. And then new legislation and the war in Ukraine prompted a speed up in the deployment of those technologies at the same time that nuclear was retired in the country. So it's not a continuous, not continuous trends, despite needing to get to net zero and with actual targets to do that. Similar issues in Spain and the UK, where in Spain government subsidies weren't passed through to consumers, and so that led to a tariff deficit and an abrupt stop to government support and loss of jobs in the wind sector, and so that of course slows down wind deployment, also solar. And then similar issues in the UK. In this country, rising community opposition has led to county and state level restrictions on renewables. These are some nice little graphics from a USA Today article that looked at the counties with some level of restrictions to wind farm deployment and solar farm deployment. And so these are community opposition for various reasons, well-founded or not, that they occur, and that puts a constraint on how quickly and where you can transform our electricity system and other clean energy infrastructure. Another critical bottleneck is the queues for new electricity generating capacity to connect to transmission grids. when a new generator typically connects to the grid, they undergo impact studies, which have become lengthier and more complex over time. The volume of capacity entering or requesting interconnection has increased over time, but historically, the majority of those interconnection requests are ultimately withdrawn, meaning that effort has gone into studying what the impact of those projects are on the grid, and yet those projects never make it to the grid. And then over that same time frame, the time it takes for interconnection agreements to be settled and awarded has been increasing as well. At the same time, there are long lead times for critical materials. In this case, we look at copper. Despite high prices, strong balance sheets, investment in new copper projects is relatively low. This figure here shows total lead times for bringing new copper mines online around the world, and with an average lead time of 23 years from discovery to commercial production. Of course, there are a few outliers there, but it's a long time. And that suggests that, or points to the processes that these sort of large energy and industrial companies take when they invest. They take a long time, they're disciplined in their approach to allocating capital, and they're risk averse. And that all points towards things taking finite duration of various lengths. This is, of course, 23 years is a long time, but points to issues in energy system transformation. So what I've just sort of said is that energy asset developers typically follow capital discipline protocols. So capital discipline is the multi-year decision-gated development sequence that energy and industrial project developers will take in bringing new capacity or new projects online. They typically go through a series of scoping, design and feasibility studies, negotiation of contracts, permitting, financing, construction, commissioning, all of which takes time and is decision-gated. They'll go through and make decisions whether to continue or not progressively as they progressively increase the capital that they invest. So all those things that I've just pointed towards are not things that are typically captured or easy to capture in energy system modelling that says you've got to get to net zero by this time frame by building this much stuff. So this work that we've been doing has been seeking to use new approaches to analysing our energy systems that interrogate and reflect the real-world factors that determine the pace and the cost of energy system transformation. I've got a case study today that's looking at interpreting the feasibility of modelled pathways with a new technique we're calling reverse engineering, which takes a developer's perspective on infrastructure deployment and looks at the development sequence, quantifies the cost and the speed limiting effects of that capital discipline, and then looks at how you could integrate that into system modelling. The case study is Australia's what is currently a significant fossil energy exporting system, and the potential transformation of that to a low emissions clean energy exporting, internationally trading system. Australia is the world's largest exporter of coal, metallurgical coal, second largest of thermal coal, and the second largest of LNG, recently overtaken by the US, now the largest exporter of LNG. This is the exported energy over time from Australia, which dwarfs Australia's domestic final energy consumption, and subsequently, or consequently, the emissions associated with that export also dwarfs Australia's domestic emissions. So it's an important energy system from global emissions, from the point of view of global emissions, and it's one where there's been a lot of talk some plans in Australia, but elsewhere as well, to say that we should and could transform this energy exporting system to one that is clean, based around hydrogen, green hydrogen production and export. So we're looking at that with this case study. This is some work from the Net Zero Australia project that I worked on, where we looked at what it would take to transform that system. We found that in most scenarios, these are results from one scenario, but most scenarios, the dominant energy export value chain was solar PV electricity generation to hydrogen electrolysis, a pipeline of that hydrogen to a port where it's synthesized to a shipping vector, in this case ammonia, and shipped overseas. And so this map here on the right shows that what it would take to fully displace all of that coal and gas export with green ammonia. So it's an immense system. It's not a realistic system necessarily, but it gives a sense of the scale of opportunity in terms of the need for clean energy that could be exported from Australia, but also it's a little bit scary. So the way that we've been analysing that system is to translate that modelled energy export value chain to reflect the real-world deployment characteristics by using this reverse engineering approach that creates a critical path plan for the development of one large-scale green ammonia project, reflecting that dominant value chain from the modelling. That's a system that is complex. It has a bunch of different components, would have numerous stakeholders. This map on the right shows what a configuration of one project could look like, with solar electricity generation in northwest Australia, pipeline and electricity transmission line to a port, and then where that port is Port Hedland, northwest Australia, is the port where the largest amount of iron ore passes through in the world. These red dots are iron ore mines, which are currently operating with train lines to various ports in this region. So you can sort of see that a green ammonia, green hydrogen export system has a similar configuration to existing industrial infrastructure in this region. However, that existing infrastructure was developed over many decades with strong offtake incentives from China. So the business case for developing that iron ore production it was very strong, because the forecasts of iron demand in China was so strong that it meant that could happen. The case of green ammonia is interesting, and it points to the need for there to be strong demand from countries like Japan or Korea, whose renewable resource is not as strong as Australia's, but will have significant energy demand in the future. So I'll go through the reverse engineering process. So we start from a representative value chain, that one project that I mentioned, specifications of all of its components, from renewable electricity generation, hydrogen production, various storage and pipelines and transmission corridors, shipping. That project costs about, if that were to operate in 10 years' time, in 2035, a notional investment cost of about 15 billion Australian dollars, a little bit less than US dollars. We then defined a representative development sequence for a project like that, where the project would go through successive stages of scoping, pre-feasibility, feasibility, while land agreements are negotiated, with decision gates in between each of those stages. before an approval and funding phase where contracts and permits are applied for and approved, before a final investment decision is taken, and construction and commissioning then progresses. So this is our development sequence. We assign cost and time for each of those stages. And then we sequence the development of that one representative project. These are screenshots from Microsoft Project. It's a big long project timeline. We find that that representative project will take 12 years. And then an output of that is the schedule of capital allocation across that development time. We're progressively allocating more and more capital until a final investment decision is taken, and then the majority of the investment takes place after that as construction and commissioning occurs. But this points to the fact that large-scale projects like this take time. It's significantly different to an energy system modelling assumption or an implied assumption that capacity will enter operation in 2035 without necessarily accounting for that time it takes. And so this plot here shows the levelized cost of delivered ammonia for different treatments of that capital discipline or project development. Going from an overnight 2035 cost assumptions to real-world capital discipline protocols increases the total cost of delivered ammonia by around 50%. So you're going from $40 a gigajoule up to almost $60 a gigajoule. And then what's interesting with this approach is you can then look at how differences in the project development timeline, different costs of capital, different assumptions about how the project is developed will influence that end product, or the cost of that end product. So we played around with sensitivities looking at what happens if you have procurement delays or no advanced procurement, different ramp-up and permitting assumptions, and so that changes the cost of ammonia progressively. These are very high costs. These are Australian dollars per gigajoule, but it really points to this that the cost of large-scale infrastructure, clean energy infrastructure, is expensive and it takes time. So then the final stage of this reverse engineering is to take insights from that one representative project and the scheduling and then incorporate it into system modelling. So this is a little schematic that shows how you could put this into a capacity expansion model, which is an energy system optimization tool, and separate the deployment of capacity in that tool into stages which reflect those main phases of development. So we go through definition, evaluation, approval and funding, construction and commissioning, and track those decisions and the capacity investment within the model itself. So this shows me putting that into that is an output from the capacity expansion model, tracking the decisions to go through each of the phases, and then the installed capacity coming in 2035. Putting those, or looking at how the model, looking at how those different project development assumptions look in a model. You go from the assumption of overnight deployment of capacity to stage development of capacity. Your energy system cost is significantly higher when you account for this light blue here. Is when you account for the finite time it takes for capacity to be deployed. On the other hand, if you limit the cost at which your capacity can be deployed, the effect then is to delay the transition from natural gas to green ammonia and to delay emissions reduction. So that's the consequence of capital discipline. So I'll wrap up with key insights from this approach. Firstly, that developers follow a disciplined approach to capital allocation. As they increase their capital at risk, they invest in an array of studies, impact assessments, contracts, financial evaluations, permitting activities before they may finally make a positive final investment decision, and they do that for each and every project. The consequence of that is that lead times for energy infrastructure can be less than 5 years for small modular projects and to well over a decade for large complex projects. But using this approach, a project developer's lens on energy system transformation can potentially also give us guidance for how to mitigate sequencing challenges in the energy system. For example, looking at the dependencies on enabling infrastructure can help identify investments that crowd in projects and on both supply and demand side and speed up deployment of clean energy. Or looking at finite timelines for grid connection permits, accounting for them in system modelling could then inform the benefits of permitting reforms or different stakeholder engagement standards. So this is today's focus was on finite capacity development durations. The project more broadly is looking at a whole range of speed limits on the energy transition, supply chain, labour force inertia, cost premiums, learning, and so that's just a hint towards some of the work that we're continuing with on the project. So I'll leave it there. Thanks for your attention.